My name is Bung Mietkan, and in the next few minutes, I'm going to present to you my thesis research topic, the corrosion behavior of hard facing alloy used in mining industry. Before actually going to my research, I would like to explain to you why did I do research on this topic. So the Australian economy depended strongly on the mining and oil and gas industry. In mining processes, machine parts need to handle hard mineral particles where you can think that these particles can cause severe wear or rust on the part. One way to provide wear resistance on the part is to well-deposited hard-facing alloys on the surface. And this process is found to be used intensively in many industries such as the aluminum processing industry, or oil sand, or sugarcane industry. If you open any welding handbook or standard about hard-facing electrodes, all the information about hardness on the electrode are given. Information about corrosion behavior, however, are not provided. In fact, in practice, these materials are exposed to a wide range of highly corrosive environments. Particularly in the one in aluminum processing industry, a hot caustic solution will be high supporting. Therefore, it is important to perform corrosion research on these alloys to provide guidance to the industry. And that's the purpose of my research, where I perform the corrosion research on 4 hard-facing deposits using the anode polarization test and potential catalytic test. The solution I use is sodium hydroxide with the high supporting. I try to simulate the solution used in the aluminum processing industry. All the alloy I use were chromium white iron alloys. The significant features about these alloys is that they have a very high carbon and chromium content. So you can have a look at the carbon and chromium content of the 4 alloys here. The carbon content ranging from 3 to 5%, and while the chromium content ranging from 20 to 30%. So with very high content of chromium and carbide, it benefits from the formation of a compound named carbide. That the compound formed between the metal and carbon very high hardness, and that's why these materials have a very high hardness. So typically, these materials have microstructures of carbide forming on an iron matrix, and the addition of other alloy elements, changing the iron matrix to different microstructures. Basically, we got the alloy D with a martensite matrix, and alloy 1E, 9E, and S have an austenite matrix. So using the different microstructures and different chemical compositions, I hope I can have a very good comparison between the corrosion behavior of different alloys. So now we will have a look at the microstructures of all the alloys. So as I said before, the microstructure of hard-facing alloys, typically we got carbide, which is the white region you can see on the screen here, and the matrix and the darker region on the screen. So we got a picture with a high magnification on the sides here, where you can see the carbide forming and it's sitting on the matrix. The matrix support and contain the carbide, so acting like composite materials where the carbide actually provides the hardness for the material, and the matrix provides the hardness. So now we will have a look at the test result for the anode polarization test. So the anode polarization test, basically you apply a potential to the samples and you measure the output current. The higher the output current, the higher the corrosion rate. The graph on the slide here, so we have the vertical axis is the potential applied to the samples, and the horizontal axis is the current density measured out of the samples. So unfortunately, not that I expected, all the curves are similar in this solution of pH supportive. It means that the corrosion behavior of different alloys, different microstructures, and chemical compositions are the same. So the corrosion behavior of them are the same in these solutions. However, there are 2 important findings that I found from the test. The first one is they form 2 acid forming layers. The first one is in diffusion here, second one is here. Passivity effect is when the metal can form a stable oxide component on the surface to stop it from further corrosion. And you can see the current doesn't change much at all in the right changing of potentials. So examination of the microstructure before and after the anode polarization test, showing that so the carbide in here is really tight, and you can see after the test all the carbide shows in the black region here. So the corrosion attack actually occurring on the carbide. The matrix next to it, you can see able to see it. It means that corrosion attack on the matrix actually less than the carbide. And this information actually very surprising for us because in the current literature, all the other researchers have found that the carbide is a very stable compound, very corrosion resistant, and usually count the matrix as starting to corrode for the carbide. And the corrosion of the carbide on the is very, in engineering point of view, is very undesirable because the carbide is low before the matrix, the hardness of the material is reduced, and the wear rate of the part actually accelerates. Therefore, we only have the microstructure before and after the test. So in order to see the whole process of the microstructure change in the analytic curve, I decided to do the potential static test. So the difference between the potential static test and the polarization test is that the potential line of sample doesn't change, but it's keeping a constant value at the whole test. So at the end of the test, I can remove the sample and detect the microstructure at that particular potential. So it's only showing me that on the graph here. The all the picture about the curve are for the metal with an orthogonal matrix, and all the micro picture below the curve is the martensite matrix. So basically, what it gives me is because the first potential, you can see that no corrosion happen on the surface or the matrix or carbide. When it increases the second potential, the orthogonal matrix the alloy with orthogonal matrix, so that the carbide particle is solved. And further increasing the potential, showing that the carbide is orthogonally starting to be solved before the matrix. Same thing, slightly different behavior will for the martensite matrix, where the martensite matrix at low potential starts to corrode before the carbide. But when we increase the potential to the fourth potential, the martensite matrix only covered by a thin layer of corrosion. The carbide fully dissolved already. So this means that the matrix in the martensite matrix only starts to further corrode when it increases the peak potential. So it means that when you increase the potential from reducing to oxidizing solution at very high potential, the carbide is starting to dissolve first before the sample at a solution of pH of 14. Comparing between the orthogonal and martensite matrix, martensite is more prone to corrosion compared to orthogonal, and that's the finding on my test. Next slide, showing a summary of all the tests of all the potential static tests I have done on all my samples. So from the left to right is the microstructure of each alloy at 5 different potentials. I already showed you the microstructure chain of B and 1B. B is the martensite matrix, 1B is the orthogonal matrix in the previous slide. The alloys 9E and S are the other two orthogonal matrix, and basically it showed me the same result when the highly oxidized solution at pH of 14. The carbide is solved first before the matrix. So as I said before, the dissolution of the carbide before the matrix in an engineering point of view should be further investigated because this carbide is solved first before the matrix. There is no point for using hard facing alloy, and they are not very cheap here, to track the to increase the wear rate of increase the wear resistance of the part in corrosive environment. The mechanism behind the dissolution of the carbide, though, unfortunately I didn't figure out how it actually works. But using the full diagram, I can have a possible explanation why the carbide is solved first before the matrix. Basically, full diagram is a diagram using in the industry to predict whether a material when exposed to a solution it will start to corrode or not. It's a diagram of the potential, which is the pH level. So basically, when you have the potential to get a certain solution, you know the potential, you know the actual potential of that metal exposed to the solution. So you can plot a point on the graph and see whether it will corrode or not. There are 3 regions on the diagram. Under this region is the cannot corrode region. The middle region is the main corrode region, where it can form a stable oxide phase to cause corrosion. The top region are the corrosive region where it reaches there and it will might corrode. So looking at the curve here, the first point of the carbide is sitting here. So the carbide is sitting on the cannot corrode region, so it's still stable. When you bring it to the second potential, the carbide got dissolved in the solution. The same thing will happen for the matrix where the orthogonal matrix forming the iron hydroxide table in this region, and you bring it to the peak potential, it starts to be dissolved, and corresponding to the degree of current the form 4 to 5 and form 1 to 2 on my diagram. Yeah. So findings in my research. The first one is the addition of different alloying elements to the alloys having little effect on the corrosion behavior of pH of protein. The andesite matrix appears to be more prone to corrosion compared with the austenite matrix. And the most important finding is that carbide is corrodes before the matrix in a highly oxidizing condition in alkaline environment. So this is giving a very important point for the research to further discover what is the intent behind it to further to increase the wear resistance of these materials. And that concludes my presentation. Thank you very much.
Questions for me?
A question out of left field. What would you use for face hardening material in those conditions?
What would I use?
Yeah, what would you use if chromium and carbide don't work? What would you use?
Oh. We got different. So I did test on white chromium white iron alloy. We got different half facing alloys. Unfortunately, I didn't really research on the half facing alloys now actually where application could be and corrosion research could be. And in fact, there are not much research focused on half facing electro and half facing alloys in general at all. Actually, because in research, when I do my literature research, half facing alloys can be formed in form of welding, but you can form in form of casting as well.
Yes.
So I can form a couple of the research on casting as well. But to be honest, chromium alloy is the most popular one, so I just advise on my research on that. I'm not really sure how good I am doing it, how good I feel the different materials. So, yeah.
Okay, then.
Can you please go back to one of the first pictures where you showed? Yeah, I want it for that. Yeah.
Yes.
So what's that border on your picture after? Why is not all of the picture corroded? Why not the part of it is corroded nicely, the top part one?
I want to make a comparison between the region where it's not corroding and it corroding, because when I do the test, so the sample, quite a sample like this here, you only expose certain areas on the sample to the solution, so only that area is corroding. The area outside of it, so that picture taking as a border of the corrosion areas on my sample only. So that's why I have to look at the other half of the sample and the other half of the picture and corrosion rocks. And one point though, because that actually, because I use a rubber ring to solve the solution from escaping my electrical cell. So because the test is done in quite a long period of time, around 4 hours, it's possible for some of the sodium hydroxide solution to get into the ring between the areas, and at a less concentration, the corrosion happen at a lower rate. That's why you can see the matrix here, but you take the picture at the middle of the area, you couldn't see any matrix or carbide or the corrosion. I want to solve the clearly the carbide is so close to the matrix, that's why I solved the picture at that level. But if you just I can solve more picture again.
I may have missed something saying on this slide, your graph there.
Yeah.
What was on your horizontal axis and what was on your vertical axis?
So vertical axis is the potential we apply to the sample, where the horizontal axis is the current density that is measured from the sample.
That's the result of that.
Yeah.
And they all are very similar. Can you explain why that graph has approximately that shape?
Okay, yeah, so because if you come back to, I would better explain it with the